In this video, we'll learn about the law of multiple proportions and how to name molecules and compounds. It was first observed in chemistry that when atoms combine, they always seem to have a certain ratio to each other. And it was always a whole number ratio. There were no fractions. It was all integer numbers. And this led to the idea that atoms must react in a certain way. You can't have half an atom. You either have one atom, two atoms, three atoms, but there's no combination which results in 2.5 atoms. You either have two atoms or three atoms. And this led to the development of the atomic theory of matter and the law of multiple proportions. Now, when compounds are formed, you have two elements combined in a way that has some sort of whole number ratio of atoms to each other. For example, oxygen in the presence of nitrogen will combine to form NO, nitrogen monoxide, with a ratio of nitrogen to oxygen being 1:1. Now, when we talk about molecules and compounds, we're talking about being able to write these materials using chemical formulas. And chemical formulas are just shorthand notations which scientists use to convey what they're working with. And so we have to be careful when we're working in a chemistry lab to make sure what we think we're working with is really what we are working with, because there are subtle differences in the names of materials. Every chemical will have some sort of chemical label on it indicating the danger and any safety issues that you should be aware of. And sometimes it's the difference between one or two letters in a name that can mean the difference between a safe experiment and an unsafe experiment. So in this particular situation, two people were injured extracting a chemical in a plant, and because they weren't paying attention, they caused about $80,000 worth of damage to the lab. So you really have to be anal retentive and a little bit paranoid when you're grabbing chemicals off the shelf. Now, the way we write chemical formulas is we indicate the symbol for the element followed by how many of those particular atoms there are right after writing that first symbol. So in hydrogen's case, we would write hydrogen followed by a 2. Water, you can see, is H2O, meaning that there are two hydrogens, one oxygen. Carbon monoxide, we have a single carbon and a single oxygen. And when you have just a single atom, you don't need to write a 1. That's the only time you don't need to have a number following a symbol. Now, chemical formulas have several different ways of being named. We have molecular compounds, for example. These are materials that contain nonmetals bonded to nonmetals through a covalent bond. That is a bond that is the result of sharing electrons between two atoms. And when we talk about molecular compounds and we're talking about these non-metal formulas, we have a very specific set of notations. Now, before we get into that, what we need to do is we first need to define how some of the atoms exist just naturally. Because when we have hydrogen and we have oxygen, or we have a chunk of sodium, they don't actually exist as single atoms. So the first thing you need to remember is all metals, we don't actually write the specific number of atoms in a metal when it's just written on its own. So like I said, with a chunk of sodium, it has the same properties whether there's 1,000 sodium atoms there or 10,000. And so metals are generally just written as the symbol. Certain nonmetals, however, come in very specific sets. So the far right-hand side of the periodic table is known as the noble gases. That very last column going top to bottom, starting with helium, is the noble gases, and those are the only elements that exist as a single atom. Everything else is two or more atoms when we find that particular element, or we write the formula for that element. Now, there are 7 elements which naturally occur as an atom bonded to itself. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Whenever we're talking about these elements just on their own, then we always write the symbol followed by a 2 in the lower right, indicating that there are 2 of these atoms bonded together. So these are the 7 diatomic elements. And if you remember to have no fear of ice-cold beer, then you can use that as a way of remembering which particular elements have or are diatomic elements. Now, we have molecules and we have compounds, and there's some subtle differences between the two. Compounds are the result of ions coming together to form neutral materials. So that is, every positively charged cation is counteracted in some way by an anion or group of anions. And compounds always exist with discrete ratios of cations to anions. Again, they're whole number ratios. When it comes time to compounds, we simply write what's known as the empirical formula. That is the lowest ratio of atoms relative to each other. So anything that's ionic, anything that's a compound, you always have the smallest ratio of atoms to each other. Molecular formulas, on the other hand, give the exact number of atoms for each element in a compound. And these are reserved for molecules, like the name implies, because molecules are formed mostly from nonmetals. It's pretty rare when you have a metal in a molecular formula. And so for this class, we're just going to ignore those particular molecules. We won't see any of those. So molecular formulas have the exact number of atoms in it. They don't represent a ratio. They actually tell you how many atoms of each element are present. So when we write formulas, whether it's a molecule or compound, we need a way of representing it. And there are a number of different ways in which we can represent a molecule. So we have several different formulas. We have the molecular formula, which is just the symbol followed by the number of atoms of that element. Then we have a structural formula. We'll learn how to draw structural formulas later on in the course. But structural formulas simply show how atoms are attached to each other. We have a perspective drawing, which is a way in which we show how atoms are attached to each other and represent the varying trajectories of those atoms in three-dimensional space. We have the ball and stick model, which is just a slightly more graduated form of the perspective drawing, where we actually use different size balls to represent atoms, and the sticks between those balls represent the chemical bonds. Then we have the space-filling model, which is really just giant spheres representing the atoms, and the bond is implied to be there. So this is more of a structural or three-dimensional surface perspective, and you'll see that too during the course of the semester, although not too often. Mainly we'll stick to perspective drawing, structural formulas, and molecular formulas. So let's talk a little bit about our ions. Ions are the result of atoms gaining and losing electrons. Cations are formed by an element losing an electron to something else. It has been removed completely from that atom. So cations are positively charged ions. They have charges in whole number increments, so you can't lose half a charge or a quarter of a charge. And cations typically form with metals, and perhaps the only exception to that would be hydrogen. Hydrogen's commonly seen as a cation as well as an anion. Anions are negatively charged elements. They have more electrons than they should, and they've stolen them away from our cations. Anions are nonmetals and only nonmetals. We don't see negatively charged metals at all. It's basically the blue highlighted elements over on the right-hand side of the periodic table. And so when we talk about cations and anions, when we name a cation, we simply say the name of the element followed by the word ion. So sodium ion, calcium ion, cesium ion. With the anions, we add the term "ide" to them. So we take off the suffix, add an IDE ending. Nitride, fluoride, sulfide. And then in the middle of the periodic table, we have the transitional metals. And transitional metals form cations, but they can have multiple charge states. It depends on how many anions are paired up with it and what the charge of those anions are. So it's a little bit of a guessing game, and there's a way you can actually work that out mathematically to figure out the right ratio of cations to anions when they form ionic compounds. So ionic compounds are formed between a metal and a nonmetal, or metals and polyatomic ions, and they represent materials that are held together by electrostatic charges. That is, positives and negatives being a natural attractive force to each other. So ionic materials are composed of charged particles, and yet when we have an ionic material, the net result must be that all the positive charges are canceled out by all the negative charges. So here, if we're trying to combine magnesium and nitride together, what we need to do is figure out how many magnesiums we need to cancel out the charge coming from nitrogen. And one way you can do that is simply by looking at the charge of the cation and writing it as the number of atoms of the anion needed, and the same for the anion to the cation. So we can see magnesium needs 3 magnesiums there to cancel out 2 nitrogens. So we crisscross the charges to get the subscripts on the ionic material, and then we double check to make sure that this is the lowest ratio of atoms to each other. Well, we can't factor 3 and 2 out. They don't have anything in common besides 1, so this is indeed the lowest ratio of magnesium to nitrogen. This is the proper formula for magnesium nitride. So here we've got a number of common ions, common cations we see, and you can pause the video here to jot down or look at what our common cations we'll encounter in this class are. We've got a polyatomic cation, that's the ammonium ion, so that's NH4+. So whenever you have a cation NH4, there's always a +1 charge. And then you can see some of the other cations there. So for example, cobalt and copper. Because these are transitional elements, and because they can have multiple charges, when we describe or we name the molecule, we have to say what the charge is. So if we're talking about copper with a +2 charge, we call it copper-2 ion. Or lead with a +2 charge, it's lead-2 ion. Or iron-3 would be iron-3 ion. Then we can go over to our common anions. And again, just want to point out, hydrogen can be both a cation and an anion. And you'll know where to write, you'll know when hydrogen is positively charged or negatively charged, because when we write these ionic materials, we always write the cation first. Chemists are positive people, so we always start off on a positive note. We see, again, fluoride, chloride, bromide, these are all ions with the -1 charge. Notice, however, there is no Roman numeral naming convention system that we use for the anions. So we don't indicate the charge, we just know it. So this is something you're going to have to memorize. If you're taking the lab course, then you'll be asked to memorize a number of these polyatomic anions, as well as some of the cations and their charges. And provided that you're learning that, that should be more than sufficient for the class. So to write an ionic material, we always start by naming the cation. And then if the anion is a single element, we cut off the suffix and replace it with an IDE ending. Otherwise, if the anion is a polyatomic ion, we simply name what the polyatomic ion is. If the cation is one of those transitional elements that can have more than one possible charge, then immediately after writing the element, we put a parenthesis and use a Roman numeral to indicate what the charge is on that particular cation, and then we continue on writing our anion. I'm going to add in one other thing that isn't on the slide here, and that is when we write polyatomic anions, if we need more than one polyatomic anion, what we have to do is write the polyatomic ion and then surround it with a parenthesis, and then go ahead and place the number of that polyatomic ion outside of the parenthesis. The other type of naming of material that we'll talk about is binary compounds. So we're talking about naming materials which have two nonmetals in it, two different elements, I should say, not necessarily a total of two atoms, but two different elements in it. And the way we go about naming these binary materials is we start by finding the element that is furthest to the left on the periodic table. And then if they're in the same column, then we use the one that's furthest to the bottom. Now, unlike compounds previously, the nomenclature here is a little more straightforward in one sense, in that you are actually specifying how many of each atom there are. So we use the prefixes for 1 to 10, so mono for 1, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca, to indicate how many of each atom there are. And we always write the prefix for the element before the actual name of the element itself, with the only exception being we don't use mono if there's only one of the first element in the formula. So to name these materials, what we do is we write the name of the first element, and then we write the prefix for the second element, and then we change the ending of the second element to IDE. So CO2 is carbon dioxide. Notice we didn't put a mono there, because carbon, even though there was one carbon, we don't need mono when the first element is just one. We have carbon tetrachloride, so again, one carbon, and 4 chloride ions. And we're just specifying how many of each atom there are. This has nothing to do with ionic charge or anything like that. If we have N2O5, then we have dinitrogen pentaoxide. So it becomes fairly straightforward after a couple of practice problems on naming materials. And again, if you need help or assistance, feel free to reach out and contact me, and I can get you a little more assistance. So at this point, you should be able to start looking at your food labels and have some idea of what it is that's actually in your food. So calcium sulfate, you should be able to write the formula for calcium sulfate now.